problem on our exam, which is my pipe burst. So I had a pipe burst in my house early this semester. I was using copper pipe instead of my new PEX polymer piping. I know, really bad for my polymer course. I need PEX piping, but it's a little bit expensive. It is much more ductile, so they tend to not burst. That's why we use that now. Almost for all new houses, we'll use that. So, anyways, my pipe was 0.1 diameters, 0.1 meters in diameter, 5 millimeters in thickness. My radius is equal to 0.05 meters. My thickness is equal to 5 times 10 to the 3 meters. Below is the schematic of a fracture surface that I observed in my pipe. I'm going to write my coordinate system already. 1 in the 2 direction. According to San Joaquin County, it should have been pressurized at 1 MPa, but my pipe burst at a strain of 4%. So first it's asking, is my, well, actually before I get into any of this, I want to check, actually I'm going to delete everything in this notebook, and then be sure to, again, remember to do this when you take your exam, which is the following. So we're going to delete this, we're going to quit the kernel, and we're going to, in between each problem, make sure to do that. So let's start to define some values here. So let's shrink this. So I know that my R is going to be 0.05. My thickness is going to be 5 times 10 to the minus 3. We need to make sure that if we're thin wall pressure vessels, R over T must be greater than or equal to 10. So R over T must be greater than or equal to 10. Let's go ahead and look at that value right here. It is equal to 10, so we're perfect and we're good to go. Once we know that, according to this coordinate system that I wrote, I know that my stress tensor should look like the following. So it should be like hoop stress, my longitudinal stress in the other direction. Everything else should be 0. And then accordingly as well, I should have this equation for E times sigma H minus nu times sigma L, and strain in L, longitudinal direction, is 1 over E times sigma L minus nu sigma H. So I also know that the pipe should have been pressurized at 1 megapascal, but we're not sure. Again, that's what the county is claiming. But I do know for a fact that it burst at a strain value of 4%. So I know that because I have this expression, or we know that sigma hoop is equal to delta P R over T, and sigma L is equal to sigma hoop over 2, the pipe should burst in the hoop direction, and thus it should burst when this value is equal to 0.04. And we also know that, again, this is our hoop direction, longitudinal direction. So the hoop is larger, so this stress should be larger here. So if I pull along the skin of that hot dog, this fracture surface should be correct. If it fractures in this direction, it's saying that the longitudinal stress is larger, i.e. when we're pulling this way. That could definitely happen if there's some imperfection in the material, but that should not normally occur. If there's some micro crack or something where the stress is larger there. But generally, if the material is completely defect-free, isotropic homogeneous, that's how the material should fracture. So this fracture schematic is definitely correct from that explanation I just gave right now. Now we just have to figure out what's the stress and strain tensors. So let's go ahead and define those values. So sig H equals del P times R divided by T. Sig L is equal to sig H divided by 2. I also know that I can solve now. My E sub H is equal to, right when it fractures, if I want to find, again, what's the stress state right before fracture, I could solve as well for solve E sub H, set that equal to 1 over, what is my Young's modulus in this problem? Well, I'm working with a copper pipe, so I'm going to just assume that E is equal to 100 gigapascals. That's a good assumption for metals, and nu is equal to 0.3. So I'm going to define those right here. So Y equals 100 times 10 to the 9th. And then, I'm going to also do nu is equal to 0.3. So 1 over Y times sig H minus nu times sig L. And I'm going to solve for del P. That is my only unknown left in this problem. So this is my del P. Del P equals the following. So now I have my sig H, my sig L, and what's my EL? Actually, I know. Let's go ahead. EL equals 1 over Y times sig H minus, sig L. Sig L minus nu times sig H. And there we go. That's my EL. That's my my sig EL, my EL here. My strain in the longitudinal direction. My strain in the hoop direction is at 0.4. So that's the stress and strain tensors quantitatively. Determine the principal stress state. We know that we're already in the principal stress state, so that rotation will be 0 degrees. What about rotation to get to maximum shear stress state? That's going to be 45 degrees. Again, more circle, or you could can confirm that with your dotting it with your t value as well. So because we know actually that for our shear stress here, we know that for thin wall pressure vessel, hoop, longitudinal, and then 0. So those are going to be my eigenvalues. So my maximum shear is going to be sigma h minus 0 over 2. That'll be my maximum shear stress in the entire 3D more circle. Actually, that's what the problem's asking for. I didn't even realize it right there. And then finally, what was the real pressure in my pipe? We see that the pipe pressure is 4 megapascals. So that was definitely not true. Or actually not 4, actually 470 megapascals. So very, very, very untrue from San Joaquin County. So they should pay for my pipe bursting. Unfortunately, that was not the case. So that's all. That's question 2. So next time we're going to get into a little bit of a more difficult problem. Actually, we encountered something very similar in the video that's already been posted, but we'll go through that problem again for composites, and then one more problem on our one more problem concerning. Oh, excuse me. One more problem concerning our basically dynamic mechanical testing, and that's it. All right, I'll see you all in the next video. Thanks. Bye.